Good morning. Today we are moving into chapter 29. Chapter 29 has this intimidating, terrifying title, Electromagnetic Induction and Faraday's Law. So, and the picture they've got here, this is, well, this looks kind of like a coil of a bunch of wires. We actually have that in some of the lab equipment. And there's a magnet that person is holding, and as the person moves the magnet, it actually is generating a current. So, you know what this chapter should really be called is Let's Generate Electricity, because that's what the chapter actually is about. So the chapter is taking a look at how electricity is generated. Now in particular, how do we get a current to begin moving in a wire? How do we generate a voltage or an EMF? Same thing, we're using those interchangeably here. How do we generate an EMF so that there's a push that will maintain current, transfer energy through the wires? Electricity is so useful. How are we to get that generated? And here's kind of the most basic idea. I always feel like textbooks tend to put the emphasis in the wrong order here. They start out with this, what I feel like is a more complicated approach, Faraday's law, and then they come back later and do this simple approach. I'm going to start with the simple approach first. So I'm going to say, this is it. This is how we're going to generate electricity. Let's say that we have a magnetic field. So I got my magnetic field set up. I've got some wires running along the magnetic field over to this light bulb and then back over on this side. And the wires are set up in a way where when I take this other piece of conductor, so I've got another conducting piece of material, and I'm going to move this conductor piece back and forth in the magnetic field. Now when I do that, there's going to be a current generated. That's all we have to do. All we have to do is set up a magnetic field and then move this configuration of wires back and forth through the magnetic field, and we'll generate a current, and here's why. If I take a look at that bar right there, the one that's moving through the magnetic field, it's full of protons and electrons. Now, as I'm pulling in this direction, there's going to be a force on the protons in this, I hope I got this right, let's see, right-hand rule, velocity, magnetic field, force, that's on the positive charges. And then for the electrons, well, I could use a left-hand rule. So velocity, magnetic field, force. So what's going to happen is the protons get pushed in that direction, electrons this way. This happens every time anything is moving through a magnetic field. The protons get pulled in one direction, electrons get pulled in the other. I'm sure you've all experienced this walking through Earth's magnetic field. It can be kind of annoying at times, right? All your protons are pulled in one direction. And anyway, what happens then is I've got all these electrons lined up in here, and if it's a conducting piece of material, well, those electrons can move, or at least some subset of the electrons are available to move through those wires. That says, if I push on the electrons and they actually begin moving, I'm transferring energy. I am doing work or transferring energy into those electrons, and we can calculate how much. So I'm specifically looking at the electrons, since they're the charges that are going to be mobile. Protons aren't going to move as a result of this. And the force that is being exerted on those electrons in a magnetic field are given by Q times V times B. Now there's a sine theta factor in there, but from my force diagram, from my cross product diagram, I can see that the angle between the velocity and the magnetic field in this setup, I guess that's the diagram right there, that's at 90 degrees. And so I'll drop the sine theta and just say, hey, there's a force of QVB, and it's pushing, if I follow an individual electron, it pushes the electron all the way across the length of L, where, here it is, L is the length of that piece of material. Well, that means the energy transfer, the amount of energy I've transferred into that electron, is Q times V times B times L. And that energy now is in the circuit. And it's available to go light up a light bulb or heat up a toaster or something like that. Now, we're more interested in, rather than in terms of energy, we want to get back to voltage. We want to get back to EMF. The EMF, or voltage, that we generate, we can get by taking the work and dividing through by the charge, and that leaves us with V times B times L. And that's it. If I take a setup like this, and I move a wire of length L through a magnetic field region at velocity V, I'm going to generate an electric potential. I'm going to generate an EMF, and that EMF will be given by V times B times L. Now, what if we want to make this alternating current? What if I want to have this generator, this very simple generator that we've defined, how would I turn that into AC? And what I could do is I can have the velocity time varying. You know, I can only go in one direction so far, so then I could come back, and so I could actually move this bar back and forth in the magnetic field in a sine fashion. So there's going to be some frequency of oscillations, and the velocity is going to continually be shifting. If I plug that into my EMF formula, what I get is a voltage that has some peak value times the sine of omega t. Alternating current, done. That's it. That's the end of the chapter. It could be. There's some more details that we want to look at within the chapter. But that's the basic picture of generating EMFs. Now let's take a look at some other features or properties of this generator that we've built. So again, I've got this magnetic field region. Now the wires are going to get connected to this bar, but I've really just drawn the picture of the bar, and let's here's our plan. Let's build a generator that will produce an EMF of 120 volts, just like the outlets, frequency of 60 hertz, just like our outlets. Now it turns out that at 60 hertz, if we convert that over into radians per second, it comes out to be 377. So I want an omega value of 377 radians per second. So we could go around to all the appliances that are listed as 60 hertz and cross out the 60 hertz and write in 377 radians per second, put those in standard units if we want. So I'm going to do this. I'm going to go in and say, look, how far back and forth would this bar need to move in order to create a generator with these specifications? So I put x as a function of time, and I'm going to oscillate it as a sine function. And then the voltage is given as the time derivative of that displacement function. So we're kind of back in oscillatory motion, looking at equations for displacement and for velocity of the bar as it's going back and forth. Now, the omega times a, that is my peak velocity. So the peak velocity is given by omega times a, where a is the amplitude of the oscillations. Now, let's assume this. Let's say we have an external magnetic field of 2 Tesla. That's got to come from somewhere too. And that the length that we have here, let's say that's 0.80 meters. Well, let's come back to this side. Here is my voltage then, or my EMF that's being generated. That's going to be given by V naught, B times L, times the cosine of omega t. And what we've done there is we've taken this expression and plugged that in to V times B times L. The same thing we saw on the previous slide. So that's going to give me voltage then when we plug in for V naught. V naught is going to be given by omega times A. and it says the peak voltage of my generator needs to be omega times the amplitude of oscillation times the magnetic field times whatever the length of that bar is. Now, if you remember, the voltages that we have in our outlets, they're listed as 120, but that's a type of averaging. It's an RMS averaging that we use. The peak voltage of our outlets is actually larger by a factor of a square root of 2. So that means I really want these specifications, I guess. I want an omega of 377 radians per second, and I want a peak voltage of 170 volts. So, and then this is my formula. Peak voltage, omega A, B, L, and the omega is set, since I want 60 hertz, it's got to be 377 radians. And then I just started imagining some other possible numbers. What if we have a magnetic field of 2 Tesla, let's put in a length of 0.8. When I did that, I was able to solve for the amplitude. So the amplitude I came up with was 28 centimeters. So that says, if I build my generator, and I have a magnetic field of 2 Tesla, and I've got a length in this direction of 80 centimeters, and then I have to allow for 28 centimeters in either direction of amplitude as the bar oscillates back and forth, that's it. We're going to have our generator, and it's going to be producing 120 volts RMS, and it's going to have oscillations at 60 hertz. Now, that's pretty fast for that bar to oscillate back and forth, right? That bar's got to go back and forth 56 centimeters, and it's got to do that 60 times a second. Is there an easier way to get that done? And there is. And so the way generators are built is you don't move them back and forth in a plane. What you do is you attach this bar and many other bars, a lot of wiring, to a rotating system. So you get something that's rotating, and so what's happening is this, oh sorry, wrong direction. It's rotating along a rotational axis. So rather than this being the center of oscillation, it's the center of a rotor. It's the center of something that's going around in circles. And I'll get the same voltage, I'll get the same effect, because if I'm going around in circles, the portion of that velocity, is going to be the v sine theta component. And the v sine theta component is going to behave just the very same way that that the oscillations, when we put in this factor of cosine, whether we express this in sines or cosines it's kind of the same thing. It's an oscillatory sinusoidal type of function. So yeah, again, I want to say done. You know, we've seen how generators are going to work, and it wasn't so complicated. We just had to move a conductor through a magnetic field. But there's another item we should take a look at, and that is, okay, here's my light bulb, here is this bar, here are the wires that are going to be attached, they're flexible wires, and we're going to move this bar back and forth inside this magnetic field. Here's that same diagram, so it must be important. So here we are, here's the velocity vector at some instant, here's the force on the positive charges, force on the negative charges. What we found in the previous slides is we're generating an EMF that's given by velocity, magnetic field, length of the bar, and that says that since I have an EMF, it's just going to behave the same way as a battery. So we've looked at batteries as voltage sources, and now we're looking at, or EMF sources, we're looking at generators now as EMF sources also. And so when I'm moving in this direction, essentially what I'm doing is I'm creating a positive terminal and a negative terminal along that length of the wiring. So the ends of that could be considered a positive and a negative terminal. Everything else we've solved using batteries can now be Well, we can unplug the battery and plug in a generator in its place. It's going to behave the very same way. So if I've generated a certain EMF using this generator, I can divide that through by a resistance, for example. Let's say that the light bulb right here has a certain resistance to it, 10, 20 ohms, whatever. That says that the current then is the EMF over the resistance, which means the current is going to depend on VBL. How fast am I moving that bar? Moving faster, going to give me more voltage. It's going to give me more current. So that's the voltage divided by the resistance. Now, what I'm guessing is, and at the top of the slide here, is that when we have a generator, we're going to have to put mechanical energy into it. It's not going to just oscillate by itself or rotate by itself. We're going to have to put mechanical energy into moving the generator, and that's what happens in a power plant. If we have a hydroelectric dam, for example, we're using that gravitational potential energy of the water to turn a bunch of turbine blades, and that's what's going to keep the generator spinning. Well, let's just check and see why that's necessary in any case. What happens is, as this bar moves across, current is set up in the wiring. So now I have a current that's going from, well, in this diagram, bottom to top. It's going in that direction. And then we have to bring in a second force diagram. So what happens is, if I've got current going in this direction, and I have a magnetic field, the magnetic field is still there, then I'm going to have forces in this direction. So I've got these forces listed, and they're opposing. I'm going to call those resistive forces. So we got the charges moving, and that gave us a voltage, or gave us a current that was moving through the wiring. But once the current starts to move, then I'm going to have this resistive effect take place in my generator. So what that's saying is this. Let's come back to our circuit. Let's put a switch in here. Let's open up the switch. If I open up the switch, that will stop the current. Now the voltage will still get set up, just like a battery that's sitting there on the shelf, not connected to anything. So I could move this through the magnetic field. I'm generating a voltage difference, or an EMF, but it's not being utilized. There's no current that's going into motion. And if there is no current going into motion, then it doesn't take any effort to move that bar across. If I make that really smooth and kind of frictionless, once it starts moving, it'll just slide across by itself. But when I close the switch, then current is going to start moving in the wiring. And if current's moving in the wiring, that means that I'm going to have a power, an electrical power, that's V times I. Whatever the EMF is, times the rate of current flow through the circuit, is the amount of energy being generated in my generator. So where is that energy coming from? How am I getting energy into my circuit? Well, I have to offset this resistive force. So I'm going to have to push with a force that exactly balances my resistive force at all times. If I want to keep the generator spinning at the very same speed, it's not going to let it slow down, then even ignoring frictional effects, I am going to have to push on that bar with a force that exactly offsets the resistive force. And we can take a look and see how much resistive force we've got. The force is ILB. That's coming from chapter 27. The mechanical power, the rate at which we're putting energy in, can be written as F times V. So that would be the force times the velocity. Oh, here it is. So mechanical power, F times V. I'm going to substitute in ILB times V, VBL times I. This is how much force I'm going to have to be pushing with. And when I write it as VBL times I, well, that's the same thing as VI. So I know I put down at the bottom, no free lunch. Sometimes there's free lunch, right? You can get your friends to pay for it. But in any case, what it's saying is if I'm going to get, 1,000 joules of electrical energy generated in my generator, I'm going to have to put 1,000 joules of mechanical energy in. The rate of energy going in mechanically is the rate at which we're generating electrical energy in the generator. All right, let's put some numbers in and see what we've got here. Here is my light bulb, here is my generator. I'm pulling with this force, and it's moving at some velocity, and this force is maintaining the velocity because I've got this resistive effect of a resistive force. Let's put some numbers in. Let's say that we move this at some point. This is moving at 20 meters per second. The length here, 0.40 meters. I'll use a 1.50 Tesla magnetic field. And I'm going to say that the light bulb has a resistance of 4 ohms. So we got all the numbers we need here. Let's do some calculations. Well, the voltage, or the EMF, that this generator is producing is going to be V times B times L. I put all those numbers in, check all the units, and they come out as 12 volts. So hey, I got a 12 volt generator, which is going to be able to do the same thing a 12 volt battery could do. In fact, I even put plus and minus signs on the terminals of this. So I'm thinking, yeah, it's kind of like having a battery. As far as the current that we're going to get, that's dependent on the EMF divided by the resistance. That's my 12 volt generator operating a light bulb that is 4 ohms. That means I'm going to have 3 amps of current going through that circuit. Now V times I is 12 volts times 3 amps, that's 36 watts. That's how much electrical energy is being generated, or more specifically the rate at which electrical energy is being generated. So I've got this 36 watt light bulb that is, or I've got a light bulb, let's say it this way, I have a light bulb that's a 4 ohm, and because it's attached to a 12 volt battery, that works out to be, its brightness is going to be 36 watts. That's the rate at which energy is being utilized in the light bulb. Now let's go back and calculate, how much mechanical power are we going to be using? We're going to have to put some mechanical energy into this to operate the generator, and we kind of know the end of the story here, right? We did this algebraically on the page before. I can start by calculating the force. I want to see the numbers. I times L times B. Now we determined that the current is 3 amps, the length was 0.4 meters, the magnetic field 1.5 Tesla. When I put those numbers all in and check all the units, it comes out with a force of, hey, it's not so much, a 1.80 Newton force. That's it, just a couple newtons is enough to keep this moving at this speed through this magnetic field. Now, if I'm pushing with a force of 1.8 newtons, and the velocity, the bar's actually moving, 20 meters per second is pretty fast, then that's 36 watts of mechanical power. So 36 joules per second is the rate of energy going in mechanically. I've got to come up with that somewhere. I've got to come up with some kind of mechanical energy source to keep my generator operating. All right, so that's, I'm going to say, again, kind of done. We've looked at all the stuff we want to look at as far as what are the basics of a generator, what are the simplest ways of looking at it. Now, you guys remember Gauss's law and you remember Ampere's law? They were kind of these theorems that you could use when you had enough symmetry. When you had enough symmetry in the setup, it was possible to use these theorems as kind of a roundabout way of determining electric and magnetic fields. It wasn't doing a direct integration, but it was a theorem that guaranteed if you could get the setup configured in order to use those theorems, that was pretty useful in calculating electric and magnetic fields. Well, it turns out there's actually 2 more of those. There's 4 of those theorems, they're combined, they're referred to as Maxwell's equations. And so this is the third of Maxwell's equations. And it's called Faraday's law. So let's see, Gauss's law for electric fields, Ampere's law for magnetic fields, and now we're going to use Faraday's law. And what Faraday's law tells us is that there's an EMF, and there's my fancy EMF symbol. The EMF can actually be shown to always be correlated with some kind of a change in magnetic flux. So that's kind of interesting. I mean, it's kind of really surprising. But let's see how that works. So, and again, if we've got some number of loops, so they wrote the n loops over here and this somehow ended up on this side, then I can, let's go see what this is all talking about. Because it's new. It has kind of the same feel as Gauss's law and Ampere's law. This third Maxwell's equation, Faraday's law, starts out first of all by determining what is magnetic flux. And magnetic flux comes from integrating a magnetic field over an area. Now, we integrated electric fields over surface areas in Gauss's law. Let's see how this one compares. So what it's showing is kind of the setup we had before. And this is showing that if I've got some magnetic flux, so I got a magnetic field, and it's passing through a certain area, I can calculate that magnetic field flux kind of the same way I did electric field flux. And as this goes into motion, I could think about it this way. I could say, you know, what's happening here is that as this bar moves across, I am picking up more and more magnetic flux. The integration that we carry out for flux, we define some kind of a boundary. So the boundary in this case is the boundary of my circuit. So there's my circuit loop. And since that bar is moving, that boundary keeps increasing. And since there's additional magnetic field in those areas, the flux will be increasing. And I know what you're thinking is, yeah, but it's a bar going through a magnetic field. That's what's generating the EMF. But what we can show is that reliably, if the flux is changing, we can relate that to the amount of EMF. In some problems it becomes a shortcut. In other problems it's easier just to use the direct approach. So again, what we're going to say here is the flux. The flux comes from taking the magnetic field and integrating over some area. And what we're doing is we are saying how is that area varying with time. Now what they're showing in this is that from that diagram we saw before, what we can think of is that this dx dt is telling us how fast this is moving, and what we're saying is that the flux, in this case, I have a uniform magnetic field, but the area keeps increasing. So I've got some rate at which the area is increasing, and the area is given by L times, or dA is L times dx. Anyway, they're showing that we get the very same formula. So Faraday's law works under the conditions that we've already looked at. Now here's a more detailed look at flux. Let's say we've got a region. Here's the magnetic field region. The magnetic field is oriented in a certain direction. That's one of our vectors. And then the other piece we have here is an area. Now if I want to get as much flux as possible, and again we saw this with Gauss's law, if I want to get as much flux as possible, what I want to do is get the field lines so that at where the area is defined, the field lines are perpendicular to that plane. They're lined right up so that they, as many field lines as possible, pass through that area. Now in this diagram, the magnetic field isn't lined up with the area vector, it's actually tipped. So I do have an angle, looks like 30 degrees or something, an angle between where the magnetic field is and where the area vector is for that area. Now the magnitude of the area we have here is, in this case it's a square and they're writing it as L squared, but there's going to be a magnitude of area and then there's going to be a direction of area, and that vector is perpendicular to the surface. So another example of coming in and using area vector definitions. And when we take the dot product between the area vector and the magnetic field, what that's going to do is it's going to pick up the component of magnetic field that's in the same direction. So that's how flux works. So here's a problem. So let's say we have an area A2, and then I've surrounded that with some wiring. So here is some wiring all the way around. And what we want to do is calculate what the flux is that passes through the wire loop. And the flux that would pass through, now in this case, the magnetic field is directly into the board. And the area vector is also directly into the board. Or it could be directly out of the board, but since the magnetic field is going in, I'm going to decide to select the area vector to be in the same direction as magnetic field. It's going to simplify things. And so the flux that we have would be whatever the magnitude of the B field is times the area where the magnetic field is located. If there's a region where there's no magnetic field, that's not going to contribute to the flux. So even though I've got this wire loop that is really big, the entire flux is just coming from that region where the magnetic field is located. Now what if I did do this? If I have an area, I have a choice here. I can define the area vector to be into the board, or I could define it coming out of the board. And it's true, in any given problem, I get to decide which direction I want the area vector to be pointing. I have that two possibility. I could bring my lucky penny and flip it and decide heads into the board, tails out of the board. If I decide to pick the area vector out of the board and the magnetic field is into the board, then instead of having a 0-degree angle, I've got a 180-degree angle between those two vectors. And that'll give me a minus sign. So that will introduce a minus sign, but the minus sign won't change the magnitude. So we can work either way. Again, on a given problem, you get to decide which direction to define the area vector. So this flux determination, that kind of gives us the first step in calculating the EMF that we're going to come up with. So again, here's another example. I've got a group of wires. I've got N loops. And if it's oriented like this, there's no flux at all. If it's oriented like this, well, then I have a BA cosine 45. And in this case, the area vector and the magnetic field vectors line right up. So 0 degrees looks something, oh, sorry, magnetic field's the other way. So if the magnetic field is in this direction, I think I'm going to choose my area vector to be the same direction. And the area we're looking at is the plane that contains those loops. Maybe they're circular loops, right? So in that picture on the right, area vector and magnetic field are pointing right the same direction. That's 0 degrees. The difference between the two. And so for the flux calculation, cosine of 0 is going to give me 1. Here, I've rotated this 45 degrees, and in this last picture, I've rotated the area vector 90. Now, what Faraday's law is going to tell us is, if the flux through my loop is changing, which it is from picture to picture, I'm going to generate an EMF. And the EMF is going to depend on the time rate of change of that flux. Now, what you guys are thinking, I hope, is that, yeah, but we already looked at this, and what we could do instead is keep track of the velocity at which each portion of the loop is moving through the magnetic field. But that might be more complicated. This might be a problem better suited for Faraday's law. And this is just reminding us that it's going to take an external force to keep this thing moving through the magnetic field. So I'm going to say, I think we've looked at this already. The difference here is I draw the X's, magnetic fields, into the board because they're easier. And this picture has the magnetic fields outside, so the direction of voltage increase, the positive terminal, is going to be at that lower end and the negative terminal at the upper. All right, now we got to step back from all of this. Actually, maybe we'll come back to this in just a minute. Yeah, let's do this. So we looked at that example. I wanted to go through and do some numbers on this. So let's say that I've got this square loop, and I want to be able to go in and calculate what the flux is. So the flux is given by magnetic field, dot with dA. They're vectors. I got to keep track of orientation here. So in this particular picture, I've got a magnetic field times dA times the cosine of theta. That's the definition of my dot product. And the angle between the two vectors here, this is area and magnetic field, into the board. So the area vector is into the board, magnetic field vector into the board, theta is equal to 0, and that says that this flux then can be calculated as V times area for this situation. Now, if we've defined, so let's think about what pluses and minuses are telling us here. The pluses and minus signs can be used to determine which direction the EMF is in. Now, the book uses something called Lenz's law, which is a series of steps you go through and analyze, and that works too. Here's an alternate way to think about that. Think about your math classes, and if you have defined an area vector in a particular direction, let's say that you have a coordinate system set up, an XY coordinate system, and you've got the circuit loop in the XY coordinate system. Now in this system, I'm defining area into the board, so I'm going to pick the Z direction into the board. So what I've got is an XYZ coordinate system. Now in that coordinate system, if I put my thumb, and I guess this is independent of the coordinate systems, if I put my thumb in the direction of the area vector, then my fingers tend to curve in the direction of X going into Y. And starting at X and going into Y is mathematically what we consider to be a positive angle or a positive rotation. So what I can do then is put my thumb in that direction where I've defined the area vector and say that my fingers are wrapping in this direction. That means the positive direction for the EMF and the positive direction for the current in this diagram is going to be like this. Now, what would be the negative direction? If I calculate the EMF and it turns out to be a negative value, then I could use my left hand and put my thumb into that area. A left hand will tell me the direction of negative EMF and negative current. So this left-handed rotation around the area vector is the negative direction, and the right-handed rotation around the area vector is the positive direction. So negative direction, positive direction. I think it's easier than Lenz's law, but you guys can decide. So here's a situation that we've got here. Here is the loop. We've determined that when it's oriented like this, the flux is B times A. And when it's tipped this way, it's going to be BA cosine theta. So I've got a couple of different fluxes. And then Faraday's law says this in particular: the EMF comes from, first of all, coming up with a function describing what the flux looks like, and then taking a time derivative of the flux. And once I have the time derivative of the magnetic flux, that gives me the EMF. So let's say this. Let's say in going from here to here, the process occurred at some rate. So I'm going to say that the flux as a function of time. So now what I'm going to do is put the time dependence in there. I'm going to introduce a cosine omega t. So when t is equal to 0, it looks like that. And then at some later time, it looks like this. Now, the amount of EMF that we generate is going to depend on how fast we rotate this. So if I now take a time derivative of this expression, Faraday's law says if I take a time derivative, I'm going to get the EMF. And that worked out to be omega times B, magnetic field, times the area, times the sine of omega t. Now this is not a dividing sign. It's saying that the stuff in the parentheses there, which aren't there, the omega times b times a, that's giving me my peak EMF. And then what happens is, as time goes on, this sine omega t is telling me how that EMF is going to vary. So again, what we assumed here was that we started right here, and then we began rotating this at a steady rate. The omega that I have here, I'm using as a constant. And since I took the time derivative, that brought out a factor of omega. And to determine what the EMF is going to be, well, I need a value for omega. So I picked 10 rotations per second for a rotation rate. That gave me 63 radians per second. And these are just numbers I'm putting in, 0.16 Tesla. And then I just picked I think part of this was a problem that they did give on one of the slides. So putting together the omega and the B and the A gave me 25 millivolts. So the peak EMF, as we rotate this thing around, is going to be 25.1 millivolts. And then the EMF output is going to have a sine function attached. So it's like we saw with the earlier method, before we were using Faraday's law. In this situation, Faraday's law is going to give us essentially the same sort of, and here it is. Here are the numbers that are on this. So what we've got is a magnetic field of 0.1 Tesla. It's a square, and it's 5 centimeters on a side. And here they're looking at the difference between 0 degrees and 30, but I turned it into a problem where it just keeps moving around all the time. And so that's what we've come up with. Okay, so, and again, the book uses this approach called Lenz's law. And I can read this, I guess. The current that we generate through these EMF generators is always going to move in a direction that opposes whatever the magnetic field is doing. So if the magnetic flux is increasing, the current will tend to decrease that magnetic flux. If the magnetic flux is, if it's increasing, the current will tend to decrease it. If the flux is decreasing, the current will tend to increase the flux. So that's also a way to keep track of directions for this. So here it is, magnetic field, magnetic flux changes. Here's a uniform magnetic field. And what's happening is they're going to take these wires and just pull them. So you can see, going back to, again, where we started the chapter, all of these wires are going to be moving through the magnetic field region. And as they move through the magnetic field region, that's where the EMF is going to be generated. The EMF that's being generated is specifically along the sections of the wire that are moving through the magnetic field. Now, Faraday's law doesn't tell you that. Faraday's law says the circuit as a whole will experience an overall EMF, but it doesn't point to where the EMF is being generated. So that's one of the downsides of using Faraday's law, is it doesn't tell you exactly which part of the circuit is creating that EMF. So here is an induction range top, and maybe you guys have seen these. In these induction range tops, what we're doing is there's an alternating current that is in a coil, and they're calling that the burner, but it's not a burner, it doesn't get hot. What does happen is they keep, they keep changing the magnetic field, I guess is what they want us to say here. So what's happening in this induction range top is that current underneath there keeps changing direction, and that means that the magnetic field that's being generated keeps changing. Now, if a piece of metal is in a region where that magnetic field is changing, then Faraday's law says there must be an EMF being generated. So another way of looking at this is what happens is this. We have currents of wire in the range top that are speeding up and slowing down. Those are accelerations. And what we actually find is whenever charges are accelerating, they're generating fields that will have an effect on nearby conducting materials. So in this case, those charges that are accelerating down inside the coils are actually generating electric fields, and those electric fields are going to set up currents inside the pans. So that's why we need a conducting pan. We need some kind of a pan that will conduct well, because then the currents are going to get larger, and depending on how large the currents are that we set up, will generate more thermal energy. So the pan now has become kind of a heating element with currents going through it, and then those currents are generating a lot of thermal energy. So at this point, let's go back and take a look. I had put this slide aside for the time, but I do want to come back here because more and more as we get farther into this chapter, what we're going to run into is this issue of electric and magnetic fields, and what are all the different types of electric and magnetic fields that can be generated. Now, we've talked before about charges when they're in motion, when they have a velocity to them. There's a particular set of electric and magnetic fields that are being generated based on the charge, how much charge we have, and how fast they're moving. So at any given instant, we can look at how fast the charge is moving, and we can use those speeds to determine formulas for the electric and magnetic fields. Now, to a very good approximation, the electric fields are kind of independent of how fast the charge is moving. Now that's not true as you get to higher and higher speeds, especially as you approach speed of light velocities. The electric field can become quite different. But at everyday kind of speeds, the kind of speeds we're seeing for charges inside circuits, for example, this approximation works really, really well. So the electric fields that are going to be generated when a charge is in motion, that's going to be given by kq over r squared times this radial unit vector. Now, what about the magnetic fields? And the magnetic field formula that we've been working from is kq over r squared times v over c, and then there is this cross product of velocity with the radial unit vector. And so I'm going to try tipping this up just a bit, make sure we're not losing anything at the bottom. So again, this is our old original chapter 21 formula for electric fields, and this is our old well, not so old, but chapter 27, or chapter 28, I guess, formula for magnetic fields. Now it turns out that not only does the velocity of the charge determine what the fields will look like, there's also an acceleration dependent portion of the fields. And the formulas actually separate out. Now just to let you guys know, the velocity effect and the acceleration effect originate with one formula from special relativity. But they originate from the same formula, but when we carry out the calculations, we get one portion of the field that specifically depends on how fast the charge was moving at a given instant, and another portion that depends exclusively on what the acceleration was at that instant. Now we've also talked about time delay, that there's a propagation speed at which the electric and magnetic fields propagate away from the location of a charge. So this complicates things a bit too, because here's a charge zipping along, and at one instant, let's say we go in and we measure what its velocity is, and then we go in and measure right at that instant what's its acceleration. Well, then we carry out these calculations, and whatever velocity and acceleration the charge had at that instant determines the properties of the field that propagates away from that location in space. And then the charge moves on. So these fields are propagating outwards, and the charge moves to a next location. So at each location that the charge passes through, this is the full-blown story for electric and magnetic fields. At every location that the charge travels through, at that point, we need to determine what its velocity was, what its acceleration was, and then all of the fields related to that point will propagate away from that location. So as the charge moves on, the fields are still propagating away from that location. Kind of interesting, huh? How that works. So the velocity fields we've looked at a good amount. What we want to do now is, for these last 3 chapters, more and more we're going to be referring back to the acceleration effect. So the acceleration fields are different. In fact, let me do this. Let's start with the electric field. So if I have a charge that's accelerating, the electric field that results due to the charge's acceleration is given by kq over r, not r squared, but r. So the first thing to point out is the fields that are generated from accelerating charges, they don't drop off as fast. Those fields, as you get farther and farther away, they're dropping off like 1 over r squared, but these are only dropping off like r. And then, instead of depending on velocities, which these other formulas do, this depends on the acceleration, and then there's a couple of factors of c squared that make all the units match out. So a over c squared, and then it's a funny direction. So the direction of the acceleration electric field is the unit vector acceleration cross the unit vector radial, and then that vector that we get is additionally cross product with an additional radial, which sounds like a lot of work to do. The bottom line is what this introduces is it introduces a factor of sine theta. So there's a sine theta factor here, there is a sine theta factor there, there is a sine theta factor there. All of these cross products that we've written down introduce a sine theta factor into the magnitude of the field. The only one without the sine theta factor is just the straight velocity dependent electric field. Now, when we look at the formulas for the electric field and for the magnetic fields generated by accelerating charges, they're the same. They match. If you remember, we put those extra factors of C on the magnetic fields so that they would match up with the electric fields in terms of units. For historical reasons, we measure E fields and magnetic fields in different units. But we could go to a different system where instead of defining the magnetic field as we do currently, we add a factor of C on, and then they would get measured in newtons per coulomb, same as electric fields. It's an easy switchover, but and then switching over makes the formulas match up. So again, the difference between these two, they're going to be the same magnitude for acceleration. The E field direction actually wraps around the charge acceleration direction. So if the charge happens to be accelerating in this direction, then the E fields wrap around. It's kind of like, I don't know, slices of an orange or something, right? Lines of longitude. So these E field lines wrap around the direction of acceleration. So relative to where the charge is, where we're going to end up if the charge is accelerating in this direction, the general effect is that I get E fields opposite the direction of the acceleration. Now what that says is if there's other nearby positive charges sitting there, and this accelerating charge comes through, the effect of a charge accelerating through a region of other positive charges would be to push all the other charges back. The other charges will experience a force due to that E field, and it'll push the other charges backwards. So that's an effect that we want to keep track of. We're going to come back and make use of that also. So anyway, we've got these wrapping electric fields. For the magnetic field directions, due to acceleration look the same as the magnetic field directions for the velocity. We still get these loops. Now in the velocity case, the loops are oriented around the direction of velocity. In the acceleration direction, the loops are oriented, they loop around the direction of acceleration. And remind yourselves from kinematics that velocity and acceleration aren't necessarily in the same direction, right? Think of circular motion, for example. So even though these look identical, it could be that V and A are in different directions, and so these don't necessarily loop in kind of an overlapping way. Anyway, that's the whole story. So there are velocity components and acceleration components to the electric and magnetic fields, and many of the examples we see in this chapter and the chapter 30 and 31, we're going to be referring back to acceleration fields because that's what's really going on kind of behind the scenes in terms of the explanations that the textbook is using. All right, so let's get back to where we were. Here's kind of a close-up of determining direction. So how do we decide what the direction is? And again, if I've got, here's a magnetic field region. Here is a circuit. So I have a wire surrounding that region. And let's say in this case that I have a magnetic field, well I do have a magnetic field into the board. Let's go ahead and define area in that same direction. Now let's imagine this is happening. Let's say that the magnetic field is actually increasing. So there's something I'm doing that is increasing the magnetic field. And so the magnetic field as a function of time has this pattern to it. Well, if I go through now and calculate the flux also is going to be increasing. So the magnetic field is increasing like this, the flux is increasing like this. And then what I can say is, look, the EMF, Faraday's law, guarantees that if I can come in and calculate the flux and somehow determine what the time derivative of the magnetic flux is, that will provide me a way to go in and determine what EMF I'm going to get. So taking a look at the flux as a function of time graph that we have here, the d flux dt, it's a positive number. So since the flux is increasing, d phi dt is positive, and from my formula, from Faraday's law, there's a minus sign right here. And you're thinking, can't we just forget the minus sign? And we can in terms of magnitude. The minus sign, though, does tell us direction. And so the minus sign needs to be there for keeping track of direction. And it turns out that the EMF and d phi dt always have opposite signs. That's what that formula is telling me. So if the flux is increasing, or let's say this, if the slope on the flux is positive, that's the right way to say it. So if the slope on the flux is positive, then the EMF will be in the negative direction, and vice versa. So coming back over to how we've defined that, here is the area vector, and we said to determine plus and minus directions around my circuit, what I can do is I can take my right hand, put my thumb in the direction that I've defined the area vector. My fingers then will rotate in the direction of positive, in the positive direction. My left hand, if I put that thumb in the direction of the area vector, the fingers will rotate in negative. So I could, I could write negative on this hand and positive on this. You're allowed to do that for the exams. So you can write negative and positive on the backs of your hands to keep track of that. What would happen, let's do a wild and crazy thing here. What would happen if, instead of defining the area vector in the direction of the magnetic field, what if we define the area vector coming out of the page? So that would give me negative flux. If I have the area vector here and the magnetic field into the page, then my graphs are going to look different. What will happen is, as we turn up the magnetic field, is I'll have a graph that looks like this. So instead of the that's not quite right. We'll still have the magnetic field going up. Let's go ahead and continue defining it this way. But when we do the flux is going to be becoming more and more negative. So the flux is actually going to end up going negative. Now the slope on that is going to be negative, and that says that the EMF will be in the positive direction. So if I define the area vector in an opposite fashion, that will change the sign on my flux, and that says that the sign on the EMF will change. Now if I come back over to my picture, if we defined area vector coming out of the board, then what I would do is I wouldn't get rid of that X, and instead I would have the area vector coming out like this. Now in that case, if the area vector is coming out of the board, then using my left hand that has a minus sign written on the back here, this is now the minus direction, and this is now the plus direction. So as we would expect, as we would hope, there's just enough signs that get flipped around that regardless of which way we define the area vector, as long as we stay consistent with the definition of flux and taking derivatives and keep track of that minus sign, we'll get the same answer. Physically, the same answer will occur. Okay, so in this case, we're going to get the negative direction. I guess we should say that too. We never quite completed that. We determined that the EMF is going to be in the negative direction. That says if the magnetic field strength is being turned up in that direction, that we're going to get an EMF here, and the current will be driven in the direction of the EMF. Okay, what happens if we turn the magnetic field down? So let's say for a while we turn the magnetic field up, but then we turn the magnetic field back down. What happens with the flux? Well, the flux is going to follow that. So the flux is going to increase, and then as we turn off the magnetic field, the flux comes back down. Now if I look at this portion of the graph, the slope is going to be negative. It was positive while we were increasing the flux, but now it's negative as the flux drops off. And if this is negative, then the EMF is going to be in the positive direction. So what that's saying is, as we turn up the strength of that magnetic field, I'm going to have an EMF driving current in the negative direction. What happens when we reduce that field? So I had this going on, this stops, and now the current's going to get driven in the opposite direction. Now notice when the magnetic field goes constant, if V had a fixed value to it, then this derivative goes to 0. It's only during times when the flux is varying that an EMF is being generated. So again, I guess we could, one last example here. Let's say that we turn up the magnetic field, flux is going up, and then we leave the magnetic field on and it levels off, and then we turn the magnetic field off little by little. What's going to happen to the current? Well, as the flux is going up, that's positive slope, that's a negative direction for the EMF. EMF will be here. What happens when the magnetic field is maintained at that constant value? The EMF goes away. So I get current going this way for a while, and then the current shuts down. And then as the magnetic field drops off, I get current going this way for a while, and then if we leave it at 0 constant, it just shuts down again. So whenever the magnetic field the flux is constant, I'm not going to get any EMF, not going to have any current through my circuit. This is going through the steps of Lenz's law, so I'm going to leave this up to you guys. If you want to go through and use Lenz's law to determine direction, you can. You're welcome to do that. Let's practice. Here's another example of looking at directions with this. So let's take a look and see. So what's happening in this example is that we have this square loop that is being pulled out of a magnetic field region. Now, while it was in the magnetic, let's say the magnetic field region extends back here. While it was in the magnetic field region, even though it's in motion, there's no change of flux. Faraday's law then would suggest that there's no EMF being generated. Now, from our earliest formulas, where we just said, hey, a bar moving through a magnetic field, that's going to generate an EMF. If I think in those terms, so here are the two ends of this, and they're both moving through the magnetic field region. In that example, they're both generating EMFs, but the EMFs are opposing each other. So if the EMFs are opposing each other, I'm going to get an EMF here, and I'm going to get an EMF here, and the net EMF will be 0. So you can use this direct approach that we started the chapter with, or you can come back and use Faraday's law. Both predict that there's going to be no EMF generated. Again, Faraday's law just says that in a holistic fashion. Faraday's law doesn't say specifically what's happening at each location. The direct method that we started the chapter out with says that there's an EMF generated all along this length as it moves through the magnetic field. And this length also, as it was moving through the magnetic field, there was an EMF being generated all the way along here. When we calculate these two effects, it's the same amount of EMF, but they're opposing each other. So the direct method in this case, I think, provides more information. It gives us, segment by segment, how much EMF is being generated. Whereas Faraday's law just says, hey, if I look at the whole thing as a whole, there's no EMF being generated. Now, what this problem specifically asks about is what happens once this begins to move outside of the magnetic field range. Now, for this problem, we can say that the flux is B times A. It's a simple enough setup. We don't have to do any integration necessarily. We can just say B times A, and that the flux is starting off at B times A naught, and that as that square leaves the region, the flux is dropping off linearly, and then once it's completely outside, then the flux will just be 0. So again, this is specifically looking at what happens during the process where that current loop exits the magnetic field region. And what we can show is that the rate at which the flux is changing there's a time dependence to the area, and that's going to be given by minus B times L times V. Now, again, if we use the direct approach that we started the chapter with, we would be saying, of course, it's this part. Once this has exited, right, while both of them were in the magnetic field region, they were opposing each other, but once this side exits the magnetic field region, then this EMF is the only remaining EMF in the setup. And this will continue to have an EMF being generated until it leaves the region. So that says that in the direct setup, we're going to have an EMF of B times L times V during that time interval. And again, it's the time interval where one side has left the magnetic field until the other side leaves. We'll have an EMF like this. Well, the direct method works. Faraday's law works. I had written down, here is the area as a function of time. It's the original total area times 1 minus Vt over L. Once Vt equals L, then this all goes away. If we take a derivative, this is what we end up with. So Faraday's law works. Now, something that I always leave out, and you'll see this, I started by saying here's the flux. There is a factor of n. If I have n loops, then I'm going to get an EMF from each of those loops. And so what we'll end up with is if I put 100 loops in there, then I'm going to get 100 times as much EMF. So I did that. I added in the 100 factor. Don't forget that. On exams, I always have to circle it. When I first read the problem, if there's some number of loops, I always circle it because otherwise I forget about it. And I leave it out at the end of the exam. And I always lose 5 points. And so there's 100 loops. It tells us that there's 0.600 Tesla of magnetic field. The length of the bar that's coming through, 0.05 meters. And then the speed that they told us was 0.5 meters per second, which doesn't seem really fast. Let's see, kind of moving at this speed, 2 seconds per meter. That's going to give us 1.5 volts. So there you go. I don't need my 1.5 volt D battery. Instead, I will have this loop that I will move out of the field and then back into the field and then out of the field and back into the field. If this is the EMF, then we can start asking how much resistance is there. Now in this example, we are told that the resistance is 100 ohms. So there's 100 ohms of resistance, and it's not in one dedicated location. Instead, that 100 ohms is kind of spread through the entire loop. So if that's the case, then the wiring is just going to heat up. And it's going to heat up uniformly. I'm going to have the same amount of current passing through every part of the wire. There's no region where the resistance is uniformly spread through the wire. So the current we can get by taking the EMF, dividing by R. That gave us 15 milliamps. And then I can calculate the power also. So P is equal to V times I. Now notice, I don't know why it is, I always feel like when the textbook first introduces EMF, I'm hesitant to use EMF, but when I get to generators, I start calling it EMF. So watch for that. EMF and voltage here are kind of interchangeable. So power is EMF times the current, and putting those numbers together, it says that the wire's heating up and the rate of thermal energy is 22.5 milliwatts. All right, that looks like we're probably up against time here, so we'll stop here in the chapter. We'll have one more presentation, one more lecture on chapter 29, and then we will move on from that. We'll probably come back and try and review some stuff and then look at a number of new examples.